or good evening, depending on where you are attending from. My name is Kumo, and I am a course advisor for ECT. I'll also be moderating this webinar. So, before we get started, maybe in the chat box, you guys can tell us where you are attending from. And I would just like to turn your attention to the notifications as well as the sounds. So if you could just turn those off so we can minimize any disruptions that may occur during the webinar while it's going on. And secondly, I'd like to inform you that you can um, pose your questions to the professor while he's going through the presentation, and he will take the questions at the end of the webinar. So he'll address your questions at the end of the webinar. However, if you do not have the Q&A function, which is right next to the chat box, then you can always use the chat box to put your questions in there. And also, we will be giving out certificate of attendance, the recordings, as well as the copy of the slides for this webinar. At the end of the webinar, I'll provide you with the link and the QR code for this session so you can actually fill out your information and you can receive the copy of the slides and the video recording within 2 business days from the webinar. And then for the certificate of attendance, it'll be 4 business days from the webinar. And hold on, there's just someone, I just need to make an attendee because of these settings. Sorry about that. Okay, there we go. And then in terms of the event conduct, just follow my instructions and everything will go smoothly. But I would just like to inform you that you are not allowed to record this webinar because I'm already recording it and you will get all this on your email. So no need to record it. And I'd also like to advise you that with the QR code that I'll give you at the end of the webinar, that needs to be filled out within 2 days and then it expires. And after that, you'll not to get the recordings or the certificate of attendance for this webinar. Just a little bit about ECT for those of you who do not know ECT. It is affiliated to the well-established EIT, the Engineering Institute of Technology. So the Engineering College of Technology is an engineering specialist with industry-driven programs, and we offer UK recognized education. And that's all made possible by our lecturers and our instructors who are professionals and experts in the field. And also, it's been made possible by our unique delivery model. So, today's topic is going to be from sensors to digital twins, how AI is transforming industrial automation, which will be presented by our lecturer, Mustafa Jamshedian. And he will be taking you guys through this topic. And all the best. You can take it away, sir.
Yeah, good. Can you hear me?
Yes, clearly.
Okay, very good.
Thanks.
Hi, everyone. Greetings from Western Australia. I'm located in Perth, in Western Australia, and I think now it's 4 p.m. in Perth. What we have today is, as the title implies, we are talking about the transition from sensors to digital twins and AI, or the transition from traditional industrial automation to a smart manufacturing or advanced AI-enabled industrial automation. So what what I'll present today is I'll start by providing the context. Maybe 10 slides on the traditional industrial automation for those who know IA will. It's just a refreshment. I mean, it's just a refresh. And for those who are not familiar, maybe it's just a quick introduction. So here is, first of all, why we say industrial automation is changing. Because the research shows that, what happens in industry is following the research. So the research from the industry, from the people within the industry, the trend shows that um, the AI-enabled industrial automation is accelerating, and you can see the trend here. So if you look closer, the first one is the blue one is the number of publication or the number of research that are being conducted across the world on predictive maintenance, AI-enabled predictive maintenance in industrial automation. Orange is quality control. We have process optimization. And the two emerging topics or notions are digital twin and the edge AI, which I'll focus mostly at the end of the presentation. So what happens is that industrial systems, even the traditional ones, the PLCs, are generating a lot of data, right? But this data now, I mean, in traditional automation remains within the field. It doesn't go beyond. What ML can do can analyze this data. If we make use of this data, ML can analyze this data. By ML, I mean machine learning or AI, can analyze this data to make wiser decisions, to optimize the processes, and to apply predictive maintenance. And AI can be supplemented by digital twins, which are digital replicates of the physical systems. And I'll tell you in a few slides what is digital twin. And we have also edge AI, which is AI in the factory, not AI in the cloud, not AI far away from the factory, to create faster decisions and create faster feedback from the AI. And I mean, with these things, I mean, I just quickly introduced some of the, very famous concepts in smart manufacturing. With these things, we can move away from traditional automation towards the smart automation. So the most important feature of the traditional automation, I think, let me take the pointer, just a moment. Okay, good. So, yeah, I'm here. From traditional automation to a smart automation, the most important feature or the main feature of the traditional automation is the fixed rules of the control logic. So in PLCs, the rules are fixed. They do not change with changing the input or output. We have a set of programs which are run and execute a set of commands to prepare an output to be sent by the PLC. But in a smart automation, on the other hand, we have data-driven learning and prediction. So depending on the input data, we learn and we make predictions, not based on fixed rules. But it's not, I mean, the industrial automation cannot be replaced by AI, because the control remains essential for stable physical operations and for reliability. So the thing here is that AI is an enabler. It's not a replacement for current industrial automation. And by the end of this presentation, I'll provide you with the information that, automation engineers need to be supplemented to have to be able to use AI in industrial automation. AI can support decisions and can increase quality and make processes optimized. And the goal is to have informed action, but not the technology for its own. We mean that when we use AI, we need to make wiser decisions. We need to increase the profit. We need to reduce the risk by the use of AI. And that's what we will see in the subsequent slides. So what does the word smart mean? What do we mean by a smart factory? Is it just some, let's say, GPU, graphical processing unit in the factory? No. We need AI, we need AI models, but on top of that, we need a system to make AI useful. If you look at this, if you look at the figure here, this is the physical entity. For example, this can be a machine, this can be a collection of machines, or anything within the processing, or even processing line. What this produces a lot of data, and in a smart manufacturing or in smart factories, we usually have virtual entities, which is the virtual representation of the physical entities. For example, if you have a robotic arm, you can have a virtual model of the robotic arm and communicate with that. But these things produce a lot of data that should be stored. Therefore, we need connection. So communication is very important in smart factories, because communications makes the data available and usable. And on top of all these things, we need to analyze data, make decisions, and use data, not just keep data. Okay, this is the, lowest level of the automation everybody should be familiar with. What we have here is a controlled process here. The process has some input and output and some disturbances. Disturbances are always there. That's why we need closed loop feedback using the sensors, and we get the information. We get feedback from the process through the sensors, give it to the controller, or let's say the PLC, the simplest one, the simplest case. And the PLC goes through some logic, right? Some programs, and gives some output to the actuators. And then we manipulate the process through the manipulated variables, and which are given to the actuators to affect the process. But here we have, what happens in this loop is that a lot of data is being produced, and if we don't have communication with higher levels, with higher functional levels, this data remains here and not useful. Okay, so the sensors and instrumentation are the evidence layer. What happens in this lowest layer, which for example can be a single PLC, is that the instrumentation, or let's say the sensor, converts the physical phenomena directly captured from the physical world into usable signals. But the thing here is that it's very, very important. The data collection is very important, because everything you collect here will be used in subsequent downstream applications, AI applications. So if you have low quality data, inaccurate data, then the decisions recommended by AI or the AI output wouldn't be good, or simply rubbish in, rubbish out. If you don't give good information, you don't expect to get good outputs from the AI. What we usually measure in processes is, for example, the vibration, the current, the temperature, the flow, all these things are measured. But the industrial signals are often noisy and context dependent. That's why, when we say context dependent, it means that it's not, you on top of the signal, you need to collect some metadata. For example, the logbook data, the device that the data is collected from, how old is the device, or let's say when was the last maintenance work, and all these things, because all these are related to the main data. So simply saying, good analytics begins with good measurement practice. So you should be able, that's why, okay, the whole story here is that I'm trying to say that someone with AI knowledge, machine learning knowledge cannot replace automation engineer. We need to know, I mean, if someone wants to make use of AI in industrial automation, they must have, in basic industrial automation knowledge. And I'm trying here to say why and tell you exactly uh, what you need to learn, what you need to know to upgrade the current industrial processes into smart processes and make them AI enabled. Okay, this is the PLC. Many of you probably know. PLC stands for Programmable Logic Controller. This is the deterministic control. We have some input signals and output signals in and out of the PLC. And PLC has processor and memory, and you can program it, right? So this is fixed logic, fixed rules. But all these, whatever comes in and whatever goes out from the PLC is the data. And these are useful data, especially when we have anomalies, failures, and all these things. So these are very, very useful information. But the fact is that we need to use them. And how? You will see in subsequent slides. Okay, on the higher functional level, we have SCADA and DCS, supervisory control and distributed control systems. On the left-hand side, you see some schematic about SCADA. On the right-hand side, you see the DCS. What happens here is that at the lowest level, you still have all those sensors and actuators and PLCs, but at higher level, you have a collection of data. As you see, when we are moving up towards the higher levels of the control, towards SCADA and DCS, more and more data are being produced. So these are all the data that can be used, but in traditional control, it just remains within the system, or it is used very minimally. So AI helps to efficiently use the data. Okay, and as I said, communication is very, very important in industrial automation. It's the nervous system. We have different communication protocols, and this is important because when you are collecting the data based on different protocols, based on different devices, you have different types of data, right? It's not always, for example, the time series, or it's not always Excel file. So it can be image, it can be logbooks, it can be text data, anything can, go through these communication networks and gathered in the servers. And now, so far what we've seen is that we have a lot of OT or operational technology data, but we need to take this data, we need to save this data in a server, take it to a higher level, and use IT technologies to, for example, use it for predictive maintenance, use it for process optimization, and use it for, let's say, quality control, online quality control. These are the applications that I'll be going through in this presentation. Okay. So what we do is that, aside from those things, we have historians that preserve timestamp process information. These are very big data. A lot of data is being produced, and the thing here is that when we are collecting the data, for example, when we are reading the historian's data, we don't need just the raw values. We need the context. As I said before, we need to know what is the device. We need to know what is the operating conditions in other connecting equipments. We need to know when was the last maintenance. We need to know many things that are called metadata. So when we are collecting the data, aside from the raw data, we collect the metadata as well. And it's important to note that industrial data are different from ordinary data. Why? First of all, they are multivariate. For example, I'll give you a very quick example. You want to use machine learning for predictive maintenance of a motor, right? For this purpose, you need to track the current, you need to track the temperature, you need to track, for example, the vibration and all these things. That's why we say the data is multivariate. And it's often quite noisy because, I mean, for example, the vibration, it's not just the vibration of this motor. Maybe some other equipments are working around and those affect the, this signal. The other thing to note uh, about the industrial data is that failure examples, which are usually our main concern, are very rare or expensive to obtain because industrial processes are optimized or run in a way to avoid failure. For example, the corrective maintenance, the fixed maintenance, the scheduled maintenance, all these things are trying to prevent failure. That's why the failure examples are quite rare or expensive. And the other thing is the operating conditions can drift over time. For example, you create a machine learning model that works now for a new motor, but it may not work for maybe 5 years old motor. And some of the metadata, the labels or metadata, depend on expert maintenance records. That's why it's, what we want to say here is that the records that I taken, for example, the logbooks, it may be dependent on the technician or the person. And let's go to the next one. And this is where we start so far I've just presented some context, and now we are going to see how machine learning can be, or AI can be used for industrial automation. Just a very quick note about different machine learning algorithms that can be used in industrial automation or by automation engineers. One is supervised learning. These are different, the main categories: supervised learning, unsupervised learning, and reinforcement learning. These are good to know. These are the main categories. So the supervised learning is simply mapping the input to output without knowing the rules. So if you have some input and some output and you don't know the connection, so you can train some machine learning models by supervised learning so that it can relate the input to the output. Unsupervised learning is used to detect anomalies, to detect the structure without the labels. For example, you give the vibration of a motor to the machine learning model, and it tells you this is a very simple and basic example, and it tells you if it's faulty or not, if anything is wrong with the motor or not. And we also use deep learning models, which are newer compared to the machine learning. Deep learning models work mostly on images, signals, big data, and time series. And we also have, aside from these three, we have reinforcement learning that, reinforcement learning works this way. You train a machine learning by the existing, data, and then you deploy, and over time it retrains itself and gets optimized, right? This is called reinforcement learning. And a new concept in machine learning is the hybrid models, right? Because whatever we do has some physical knowledge, but maybe we are not aware of all the physics running on. So what we do is that we put whatever knowledge we have that is called physics, and we supplement it by AI so that both work together. That is called a hybrid model or physics informed neural networks or physics informed artificial intelligence. Now, I'll give you three most important examples of where AI or machine learning, mostly machine learning, fits in industrial automation. The first one is predictive maintenance. We have quality control and process optimization. These are the main three fields that machine learning fits in industrial automation. And when we say machine learning, in general AI can be supplemented by digital twins, and recently AI can be replaced by edge AI, which I'll tell you in subsequent slides. Okay, let's go through the first one, which is the AI for predictive maintenance. Just as a refresher, the corrective maintenance is the repair or when you react after the failure. The preventive maintenance is when you have maintenances on fixed schedules, right? The condition-based maintenance monitors the current condition. This is very important, the current condition. For example, if the vibration goes beyond some critical value, whether the equipment can have some residual life or not, you replace it. This is called condition-based maintenance. But the extension, the AI-enabled condition-based maintenance is called predictive maintenance. Predictive maintenance doesn't decide based on the current condition. It forecasts for you. It predicts the degradation. For example, it tells you that you need to replace this bearing in 3 months. This is called predictive maintenance. And it can predict for you RUL or the remaining useful life that supports proactive planning. Okay. What do we do in predictive maintenance? What is the predictive maintenance workflow? First of all, is the first step is the collection of the data from the machines and processes. So all the data that we described before. It can be PLC data, SCADA data, DCS data, all the data that is collected, logbook data, let's say, images, all the data from the sensors, actuators, and everything. It can be any kind of data from the factory. Then we clean the data, pre-process the signals, and extract useful information out of these signals, right? So the raw data cannot fit into the machine learning models. It needs pre-processing, it needs cleaning, it needs a lot of, a lot of modifications. Let's say not modification, pre-processing the data is required before training the models. Then we train AI model. What do we mean by training AI model? So AI model is like a black box that can learn things, right? If you give it data, give it the input and output data, it can learn from the data. You can train it, and then after training, after sufficient training, you can use it. So you train the model for fault, health state, and the residual life. Okay, so for example, you give the data for a bearing or for a motor, all the data that I said before, and then you tell it that the remaining life of this bearing has been, okay, this is not predictive at this stage, this is training. So you give the model the data that you know. So you give all the data about motor, vibration, temperature, current, the time series over, for example, the past 6 months. And then you say that this motor failed after 1 month. So this is training. And you give, for example, 100 sets of this kind of data. And after training, this model can predict for you. If you give the information of any motor, it can predict for you how much is the remaining life. And the fact is that in predictive maintenance, we can convert predictions into maintenance decisions, and we act proactively, not passively. Okay, what model can we use for predictive maintenance? It depends on many factors, but just to have some brief notes about the, I mean, different predictive maintenance models. First of all, no single best method. I mean, there is no universal method or model. We need to decide based on many factors. But some general rules are listed here. Physics-based models, they are using engineering degradation mechanisms. For example, this is physics-based models are very useful in predicting the tools wear in CNC machines, right? Because we have a good knowledge of how wear is happening in, how wear and what is the rate of wear in CNC tools. And if you combine it with AI, you can have a good prediction of the tools wear in CNC machines. Knowledge-based models encode expert rules and logic. If you are sure, for example, in robotic arms, you know the logic, you know the dynamics, and you know the rules. So you can implement all those mathematical equations and have a model for predictive maintenance. But if you don't know any of these things, you have no information, you can use data-driven models that learn purely from the data. You can have also hybrid models, a collection of these things. And in short, I can say that the choice of model depends on the data, the risk, and explainability that we see. What are these in subsequent slides? There are some benefits and challenges around predictive maintenance. Predictive maintenance can support aerial fault detection and planning. Usually, data-driven models or deep learning models are most common for time series signals in predictive maintenance. But if you have some good mathematical models or some good knowledge of the context, then you can apply the hybrid approaches. And the deployment of real-time decisions remains a challenge because, as I said, a good model is usually a big model, a big AI model that requires cloud computing. And for inline or for online decision making, we need edge AI. We need low latency decisions. That is not very easy. We see more about this in subsequent slides. Okay, the second topic, remember, I said we are going through 3 applications of AI-enabled industrial automation. The first one was predictive maintenance. The second one is quality control. Quality control, the traditional one, is like you produce parts, you produce products, and then you have a separate unit that does the quality control. But quality control in smart manufacturing is moving toward real-time assessment. You have sensors, you have image processing, you have computer vision. This is a very, very useful tool. So you have computer vision. You can see, for example, if you have 30, 40 sub-processes, you can detect early, you can detect the faults in any part at the earlier stage. So you can just discard the part and don't do the subsequent processes on the part to save money, to save time and everything. So in short, I have to be faster. So in short, quality control in a smart manufacturing is becoming real-time assessment with the help of computer vision and AI and sensors and all the, new devices that are available now. The other one, the third, um, I mean, um, the third thing that we were okay. The third thing that can be enabled by AI is process optimization, or maybe the most important one. So what we have, as I said, a lot of data is being produced, and you can extract all these data if we have connected devices. And with proper tools and models, we can analyze this data, we can apply data analytics, data science to these data and optimize the process and make wiser decisions. But these things are being supplemented by digital twins and AI capabilities. So what we have here is that we have sensors and actuators, very simple schematic sensors and actuators in the physical world, and you can have digital twins and virtual, which are the virtual representation of the physical entities. And if you establish a two-way connection between the physical world and the virtual world, then you can optimize the processes. Which much less effort and very cheap. Okay, what is edge AI? The fact that, suppose you collect the data and you have the data, but sending the data, the very simple example is when you are riding a car, right? The anonymous vehicles, if they want to send the data to cloud computing and get the response, it takes very long. It's not feasible. They have to make decisions with low latency. And it happens in many processes. For example, consider a turbine. The response should be under a few seconds to prevent failure and maybe bigger risks. So we need, instead of sending the data to the cloud and getting the response back, we need AI computing to be present next to PLC, for example, next to a SCADA system in the field. And that's called edge AI. But there are limitations here. There are, pros and cons. The advantages here are that, with edge AI, we can have local inference. By inference, we mean getting a response from AI model, giving the information to the AI model and getting the response. So this is called inference in AI community. So we need edge AI provides us with local inference, and local inference reduces latency and bandwidth use. So it improves privacy and resilience, because another issue with connected factories or smart factories is the cybersecurity and data breach. But there are hardware constraints. You cannot have very strong GPUs in edge AI. That's one of the main limitations in edge AI. Okay. And the other recent active field of research is digital twins. A digital twin or virtual twin is the virtual representation or virtual replication of the physical world. What's the use? So I'll give you a very simple example. Suppose you are planning to buy a robotic arm for automatic feeding into a CNC machine, right? So You do calculations, you do all the things that people do nowadays, and then go and buy the robotic arm and then fix it in the proper place. And after running the machine, after running the process, you realize that it collides with the, for example, CNC door. That's a very expensive experiment. What you can do is that you can have the virtual twin of the robotic arm. You run it, you optimize it in the virtual world. And when you are sure about everything, you can go and buy and deploy. That's the advantage of virtual twin, for example. I give you two applications of virtual twin. One is for virtual commissioning. You can uh, you can try different commissioning scenarios and optimize the commissioning process by virtual commissioning before commissioning in the real world. The other one is for optimizing processes. So instead of trying with the real process, you can optimize the virtual process and then take the optimized parameters into the real process. Okay, let's move on. Um, I think I discussed most of these things. Let me move on to the next slides. Okay, digital twins can be deployed across a different manufacturing level. So it can be, for example, the machine level, just one CNC machine, or it can be at the cell level, that is mostly the coordination between the machines, or it can be at the shop floor level or enterprise level, or higher levels. So at the enterprise level, if we have a digital twin, we can optimize the design, production, logistics, and lifestyle. So softwares are coming into market. Research is very active in this field, and we have many students in EIT who are working on digital twins as their um, thesis topic. Okay, as I said, we can have machine level digital twins. You have all the process data. This is the physical asset. For example, a CNC machine, you have the process data, monitoring data, maintenance data. Take all these things into the digital twin, which is the digital replication of the CNC machine, and it can tell you when will be the failure. Okay, this is the unexpected breakdown, but the digital twin can predict the failure for you, right? So this is the use of digital twin for predictive maintenance. As I said, we can have cell level digital twins, which is mostly used for human robot collaboration. And at higher level, we can have shop floor and enterprise digital twins, which is mostly used for optimizing the higher level processes and coordination among different entities. And in short, a smart manufacturing doesn't mean just more sensors or more data. It's a connected ecosystem. So when we have the data, it's not just collecting the data, it's about using the data for making wise decisions. And that's not very easy. And the other thing is that we cannot fully rely on AI to make decisions. And nowadays, like the very basic example is when using the ChatGPT. If you don't connect the ChatGPT to your inbox and ask it to reply your emails, you need to supervise ChatGPT. So the latest models for AI-driven automation is the human-centric AI-driven automation. It means that if we get any recommendations, some maintenance schedule, or these are just some examples from the digital twin or from the AI, a human, a context-aware human, a technician, and an automation engineer must confirm. We need manual verification. And also, because this is a two-way data transfer. If we have a physical device, the raw data, the physical observations, everything must be moderated by context-aware technician or engineer and then fed into the AI. That's where the AI will be useful. If you just delete the human here and connect the physical world to the virtual to the digital twin, you don't get useful decisions. You don't get accurate predictive predictions. You need the human to be here for many, many reasons. I just mentioned a few. Okay, and there are a few more things about smart manufacturing. The first thing is cybersecurity risks. So if you see when you connect things, when you send information to cloud to, IT devices, cybersecurity becomes critical. It's not just, stealing the data or losing the data, or let's say breaching some sensitive information. It's about the risk, because these data are the ones that affect the industrial processes. And because of the cyber attacks, wrong decisions, the system may make wrong decisions, and we can have something like explosions or let's say big failures in the processes. Cybersecurity is quite important. Industrial control systems, cybersecurity mechanisms. We can have different mechanisms to implement cybersecurity. For example, one thing that people use, something which might be funny, but it's real. And we have a number of students working on that as their thesis. Okay, suppose you have implemented AI for predictive maintenance, right? So one way to detect whether the decision recommended by AI is manipulated or not through cyber attacks is to have another AI model to validate the first AI model decision. That's something which is the most recent one. The the validation of AI by AI. Okay, and in industrial processes, we need, safety, reliability, and trust is very, very important. That brings the notion of explainable AI or XAI. So you can't trust, as I said, we need manual human validation or confirmation. So in recent AI models, what people are talking about is that we don't want to just get AI to tell us, for example, replace that bearing now, okay? We want the reasons. We want the AI to explain for us why do we need to make such a change, such a replacement. And that's called explainable AI, which is, the most recent field of research in AI, in AI for industrial automation. And just something very important is that there are many implementation challenges. Many projects fail because of, for example, low quality of data, because models cannot generalize, because we don't have the required hardware. We underestimate the required hardware on many reasons. So it's not very easy, but it's doable. And other important factors here are the integration barriers. As I said, we have data from different devices using different protocols, and to integrate these all these kinds of data, it's multimodal from different devices coming from different protocols. So we need methods to integrate, to overcome the integration barriers. And the future trends in industrial automation, this is, 5 different dimensions are shown here. The first one is self-learning and adaptive automation systems. As I said, because the conditions may drift over time, we need AI models that learn, okay? Not by just one run of training, that can continuously learn from the process. We need explainable AI, as I said. For human confirmation, the AI must tell us why AI is making such decisions, any decisions. Federated learning is another field of research. It means that, um, I mean, we have one AI model that can be trained by different sets of data, but people don't want to share the data, right? So federated learning means that an AI model is trained sequentially by different sets of data so that there is no breach of data or sharing of the data. Edge compatible digital twins, as I said, we need low latency decisions in the field that can be realized by edge AI, and hybrid and physics informed AI is much more robust than pure AI. Okay, and now as an automation engineer, what do you need? What skills do you need to excel, to remain top in the field? As I said at the beginning of this webinar, it's not just AI. AI, the use of AI in industrial automation definitely needs instrumentation and measurement fundamentals. PLC programming and industrial logic control remains, essential. DSC, SCADA, all the things that were there. So we are working at higher level, which is data analytics. So when all these data are collected, we can use data analytics methods, machine learning, then digital twins to make processes safe, to make them fast, to make them optimized. In simple words, to optimize the processes. And for industrial automation, what you need to learn aside from the classical automation, which I listed in the previous slide, you need data analytics, you need machine learning, digital twins, and true communication with experts in the field. We have all these things available at EIT and ECT. And the closing message here is that, just quick takeaways from this session. Industrial automation starts with, for making wise decisions, useful decisions, you need reliable and good measurement and control. Connectivity is very important to collect the data and save the data and use the data. And AI comes here. When you collect the data, when you have the data available in some servers, you can convert the data into predictions and smart decisions. And digital twins can help with smart decisions and can supplement AI to make smart decisions and predictions and optimizing the process. And the future engineer need to integrate automation. This is the traditional one with data, safety, and human interface. Okay, these are the main references which being used to prepare these slides. You can go through. We've tried to I mean, I think most of these, at least three, I'm sure, are open source. You can go there, although we have many more references. But if you go and read these four, you have you can get more information about the use of AI in industrial automation. Thank you very much. I'll be happy to take questions if any.
Thank you so much. I'm sure our attendees really learned something from this, and obviously they will receive the slides as well as the recordings. So I'm sure they'll be happy to receive that and go over it if there's anything they have missed. But in the meantime, we will be taking questions in the Q&A box. But if you don't have that function, you can always put them in the chat. So we've got about 5 minutes for that. And while we are still doing that, I will be providing you with the link and the QR code for the certificate of attendance, as well as the recordings and the slides. The link is in the chat right now. I just put it in the chat. So I just want to let you know about our upcoming courses for ECT. We've got 2 bachelors coming up in September, which is industrial automation and electrical engineering. Thereafter, the next intake will be in February. So for the Master of Science, we've got 2 as well. And the intake for this year is October. And alternatively, you can then select the February intake. And for the QR code and the certificate of attendance, I'll come back to that now. It is on the screen as we speak. So you can either take the QR code or take the link that I've put in the chat. And for the professional certificates, there's a promotion that we are currently running for our professional certificates. So those are basically our 3-year professional, our 3-month professional certificates of competency, and they purely for upskilling and development purposes. And currently, the promotion we are running will save you £334 for the course, any course you select, and that's if you apply before the given deadline. So the deadline will be the 30th of November this year. And you can always just go and take a look at that if it does interest you. The link is in the chat box for now. So you can go and take a look at that. So just a reminder, with the certificate of attendance and this form that requires you to fill it out, you only have 2 days after the webinar to complete it. If you don't, unfortunately, you will be missing out. And therefore, I would encourage you to do it as soon as possible. Do we have online, offline? We've got 3-month short courses for anybody, whether you're an international student or you're a local student. All our courses are offered 100% online. So you can go on our website and check which one will interest you. So at the current moment, we're only offering 2 masters and 2 bachelors, which I've mentioned. I can just go back so you can take a look at them. And apart from that, we've got the 3-month professional certificates of competency, which are delivered by EIT through ECT. So these are the courses that we are currently offering. If there are no other questions, then I'm sure we can just wrap it up. Is that okay with you, sir? Okay,
Yeah,
perfect.
sure. Thank you, everyone. Thank you for attending.
Thank you all
Hope you
for
enjoyed
attending.
and learned something. Thank you.
Thank you. Have a good day. Bye.